Surf is more like a velocity when you write it this way. So U is an input, X is a state, and N is going to be IID. So independent and identically distributed. Okay. And the reason for that, hey Joel, is so that it's a controlled Markov chain. And unfortunately, we have to live with the operations research language of MDP, which is Markov decision process. We'll come back to that later. But that's a modeling assumption which is never true, okay? And we do this for computational reasons, all right? And that's a really, I mean, that's a really distinct thing about control theory than any other branch of engineering, is that we know our models are terrible because we make them simple enough that we can compute something, you know. So if we're going to, you know, in aerospace, they have incredibly complex simulators based on, you know, 10th order nonlinear differential equations. But when they do the control design, they have a 3rd order linear model, you know, and they make the controlled solution so robust that it'll work, you know, even though they've ignored the nonlinearities, you know, and they know they can't model the wind. This incredibly complex disturbance, you know, hitting the airplane. So in control, we have really naive models for a very complex reality. And that's something that's really, really hard. That's one of the most important parts of the culture in control. And it's what makes it hard to talk to the real world. You know, you come up with some awesome idea, you take industry and they say, well, that's not how our factory works. Because they, you know, there's a language gap that's always hard to bridge. So this is not the sort of way you'd see, there's no textbook I could suggest that would really talk about these things the way I'm talking about in this course. I mean, normally if you have a course talking about controlled Markov chains or MDPs, you're given a Markov state transition diagram, and everything's discrete and lumpy. You hop from here, then you hop there, and you hop here, with some probability you hop there. And all the geometry and nice intuition you get for a continuous state space, and continuous time actually, discrete time is not as pretty as continuous time, goes out the window. So what I want to do is I'm going to develop theory in continuous time, where we have lots of beautiful geometry and everything, and then show you how it all goes over to the case of discrete time and stochastic disturbances. So if you understand the deterministic case, which you can blow off in one lecture, it makes the stochastic case a lot easier. All right, and yeah, and again, the thing is that, again, what I hate about it is when people go to discrete state spaces, they throw topology out the window. You know, they completely, you know, there's a point here and a point there and a point there. You can jump from here to there. And that's the mindset you get when you take a traditional course on operations research, you know, MDPs, or Markov chain course. In reality, I mean, it's hard to find examples where there isn't some continuity of states, and you want to be able to exploit that structure. All right, and so I really, in the course, I'm really going to try to stress that point. So again, this could be a pancreas or the economy, or you know, the power grid, you know, all sorts of different things. And I see your interests are quite varied, which is a good thing. So, I mean, it's all over the place. Unfortunately, I also see that most of you claim you don't know what a Markov chain is. That's scary. It's really scary. You have to catch up. Luckily, you don't need to know a lot, but you'll need to know something. So, yeah, you'll have to go and catch up. That's background that you really have to have. All right, so All right, so 3 things make things a lot easier. Forget the noise, forget the input, and work in continuous time. And so instead of a difference equation like that, you have a differential equation. It looks just like that. And I should say, I've got 11-page handout on this material, which covers way more than I'll actually cover in class. And so I'll make that available to you today. And I'm going to upload a homework assignment today onto Canvas. And hopefully you're linked up to Canvas. Don't miss these homework assignments. And I'm just assuming you know what a Markov chain on 3 states is. And if you don't, go to Wikipedia. I mean, you know, you can figure that out very quickly. Yep. And so it'll be due in 10 days. Yeah. Okay. All right. So we're just going to look at this little baby thing here, and look at stability stability and performance bounds, whatever that means for this sort of thing. Okay. So, you know, this could be an airplane, the state of an airplane, and you wanted to get it to some level flight after some transient. And you want to do that in a safe way, and you want to do it in a cost-effective way. All right. So the reason this is nice as opposed to that is I can draw trajectories. I take a particular time, x of t naught, and I want to know where it's going. Well, where it's going, I've got a velocity vector field, you know. And so you can just draw the tangent there and an arrow. And an apology right off the top. Sometimes I'm using a subscript, you notice, and sometimes I'm using parentheses. And here, I guess I was just trying to avoid a double subscript, x sub t sub 0. So at any particular time I take, if I look at the velocity, it's tangent to this curve. And, you know, and that's what you're given for a state space model. Okay, and so let's play around with this. So Anand already sort of talked about these things in a stochastic context. It's much easier here. In terms of stability, the most basic notion of stability that's most closely related to the course is ultimate boundedness. And do I really use that language? I know I'm going to get some cringes seeing limit supremum. It's the least upper bound. I shouldn't say it. It's approximately the least upper bound. A least upper bound wouldn't have the limit in it. I don't want to define it. If the limit existed, it would just be that. And in typical situations, the limit does exist. Okay, and I don't need to. I'm not going to need this concept. So I'll just, if you don't know what I mean, just say it's a limit. So for large t, I'm bounded by a constant that doesn't depend on the initial condition. All right, and that's closely related to the course because in reality we will have noise, and typically noise does pass through and makes the thing bounce around. So the thing is roughly bounded in steady state in a sense, you know. So we're going to have to take expectations here, as discussed last lecture, in the stochastic case. Okay, so that's a notion of stability that typically you wouldn't see in a nonlinear control course. You know, they would go straight to the next one, which is asymptotic stability. Now, this, just like limit supremum, I'm not going to define. I'm just going to, because Lyapunov came up with a really subtle definition of stability, so it would be equivalent to the existence of a Lyapunov function. He didn't call it a Lyapunov function. Later we did. But I'm just going to give you its main features of asymptotic stability. And I should put in global. So the most important component So first of all, there's a, I'll put an I there. There's a state for which the velocity is 0. Okay? So the velocity is 0 means if I start there, I'm not going anywhere. It's a stationary point also. And 2, x of t converges to x star. So the global here is emphasizing for every initial condition, I zoom into this stationary point. All right? So obviously there's only one stationary point, you know, because if there was another one, I'd be stuck there. You know, if I start at such a point, I stay there forever. You know. All right? The velocity is 0. So there are, again, so there are other, in the definition of global asymptotic stability, there's some other very subtle properties, and again, they're put in there mainly to get a beautiful mathematical theory. This is really what you want, you know. That is really mainly what you want. Yeah. Okay, so the term Lyapunov function came up last time, and let's look at this thing, how you would verify this. Okay, so it actually has four components. We have a function v mapping Rn to the non-negative real numbers. So Rn is what I chose as my state space for this state space model. And again, and there's 3 properties. So first of all, it's continuously differentiable. And what does that mean? It just means the gradient is a continuous function. Okay, so when I say C1, I just mean if I take the derivative, I get a continuous function. Right? Hey, I want those notes. Yeah. And so that's property one. Second, it's coercive, and we'll use this term later a lot. Here's the intuitive way of writing it down. That is, the norm of x gets big, v of x gets big. But something that is maybe less, sounds more precise. If I look at the set of x such that v of x is less than or equal to b, so for any constant b, that's a bounded subset of Rn. So I think I can squeeze it in here. So here, looking at R2, and I look at the function v of x, it's like a quadratic function with a positive definite quadratic. And if I take any value b, I'll end up getting some sort of a bounded set like that. Yeah. Stay at it for a while. Okay. And then the third property, I'll write it down abstractly. All right, so I remember when I took a course like this, and they put up there like how you could understand it, and it was like it took weeks before I understood what the hell the professor, excuse my language, what the professor was talking about. But before I explain this, first note that if x equals x star, what is this? Assuming that there's a stationary point. Yeah, it's 0 because f of x star is 0. Okay, so we can only expect this to be negative for x not equal to x star. You know, we're assuming we're at a stationary point. And what this, you know, it's pretty clear to see what this is that I take the derivative with respect to time of v of x of t. Okay, so this is the sort of thing that Anand was talking about last lecture. You know, basically looking at, I have a function of the state, and I want it to be decreasing. That is saying it's decreasing, because I used to use the chain rule. You know, the partial with respect to time is I first take the derivative of v with respect to x, and then multiply that times the derivative of x with respect to t. And the derivative of x with respect to t is, well, it's been erased. It's f of x of t. Okay, so this thing here is just saying that this is negative, which is that. So this v of x of t is strictly decreasing, you know, forever, unless it could somehow jump and hit x star, which it won't. I mean, we won't get into that. You might remember your differential equation course. You have to have a really ugly function to jump to x star. We'll get closer and closer and closer. We'll never meet it. Okay. So Yeah.
So there is only one X star, right?
Well, that's what I was saying before. If you have global asymptotic stability, there can only be one X star.
This property ensures, in a way, that there are no local X stars.
Well, definitely, because if there was any other stationary point, we couldn't get a strict inequality. Absolutely. Okay, so this implies these two properties and more. But so when I say Lyapunov function for global asymptotic stability, I mean if these three properties hold, then then we get these two properties and the remaining properties of global asymptotic stability, which I'm not going to list. It's just not really relevant for us. Okay, so that is a little outside the course in a way, but this theme of finding a function very often having, even on a discrete state space, even for a countable state space Markov chain, we're going to see it's going to have, in typical applications, it's going to be smooth, even though it's only defined on discrete points. It's going to look convex. Coerciveness we'll see is typically, it comes for free. It has to be coercive for this to make sense. And we get a million different refinements of this in the stochastic case to give us different kinds of stability. But not this, because this kind of stability, I know some people look at this for stochastic systems. On the walk over here, I couldn't even remember an example of a system driven by noise that converges to a fixed point from every initial state. What's an engineering example of that? They do exist. I just can't remember. I can't remember any. It's funny. Yeah. So typically, we're not going to converge to a point. We're going to get near some desirable region and bounce around inside that region. Okay. So UB standing for ultimate boundedness. We can get a Lyapunov function for that as well. And it's kind of intuitive. There's no X star anymore. Remember, ultimate boundedness just meant that you were eventually inside of some big ball. That's what it means. There's a one big bounded set. From every initial condition, you end up in that set. That's really what it is. So a Lyapunov criterion is you keep I and double I, but you just relax that a little bit. And in fact, I want to do two things. That's something negative. That's a function of x on the right-hand side. Let's put a bound on how negative it is. So I'm going to add another thing as well. I'm sorry. Yeah. Okay, I've thrown a lot of things in here. So first of all, if I do that, it looks just like what I have over there. I have some measure of how negative it is. Okay, But I've also relaxed the condition here, because I've got this number here, which might be quite big. Maybe it's 10 million. But it's a fixed number that doesn't depend on the initial condition. Okay? And what's typically going to happen in applications is that if I'm far away, from the center of the state space, C will be, well, it's coercive, that's right. Not typically, I've made an assumption here. If X is very far away, this will be very negative and totally overwhelm this positive part. Well, if I'm in a very cheap part of the state space, so this is small, I'm going to get a positive drift. This inequality is not so helpful. But this, I've tried to prove it in this lecture and always failed. So I don't think I'll prove it. But I'll give you some easy stuff. It gives that we get bounds on performance. Okay, so under this condition, you can prove that it's ultimately bounded. Maybe I will attempt to give you the main idea. But performance is a cost function, and there's lots of different ways we can evaluate performance. I'm going to give you one. I'll just go through and play with this, and when I'm done, we'll call what I get a performance bound. All right, so we interpret this. Remember, that's a derivative. Okay, so this is a typical trick you do when you're playing around with these Lyapunov inequalities. I have this inequality. I know that this is just the derivative with respect to time of v of x of t, if x is x of t. Okay, that's what this left-hand side is. All right, I've plugged in xt for x, so I can do that. And now what are you going to do? If you liked calculus, if you like Calc 2. Integrate. Apply the fundamental theorem of calculus. So if I integrate both sides, say from some 0 to some capital T, the integral of a derivative, the reason we assume v is continuously differentiable is so we can apply the fundamental theorem of calculus. So when I integrate the derivative, I just get the difference of functions. So the left-hand side is v of x of t minus v of x of 0. And there's an inequality here which is preserved when I integrate both sides, and I get the integral of c plus a constant. All right, and then you shuffle things around. Okay, so I'll divide both sides by capital T, so I'll get an average cost. All right, and if I divide this by capital T, I'll knock that out. And so what do? I'll put this on the left-hand side, this on the right-hand side. Just shuffle it around. Divide by T. So this and this are exactly the same. I did subtraction, I divided by t. But somewhere I said that v was non-negative valued, I hoped. I think I did in my definition. Lyapunov functions will always be non-negative valued. So So we don't, you can erase that, you know, as a negative term, I can throw it away. And the reason I would throw that away is I have no control over that. I don't, you know anything about it. And so it's better to say, well, it's positive, so throw it away. I could have said it right here. You know, that's less than equal to that, because this is positive, not negative. All right? And so there you have something really nice. So this is exactly what you get for stochastic systems, but you put an expectation in there. You know, basically we're going to get something that's almost the same as this in a stochastic setting. And we'll go through almost the same arguments, but it looks harder because you might be scared of probability. But you'll get exactly the same thing, except there's an expectation here, that the average cost is less than some steady state quantity, and then something that measures the transients. You know, as t goes to infinity, this goes to 0, but if you start off in a very, very bad place, you see how long it takes to recover from that bad initial condition. All right? Okay. Oh, steady state. I just didn't want to have to write it down. Steady state. So this is something, when you let t go to infinity, we have that the lim sup of this average is bounded by capital T. Yeah.
So you were able to get rid of the other term because you're assuming that v goes to 0?
No, v is non-negative. You know, so this is greater equal to 0. So I just,
oh, I see.
Yeah, that's all. Yeah, that's all. So this thing, I mean, if you understand this, the stochastic case is just the same. There's almost nothing at all. All right? Yeah.
What you've written there, like when we were just talking about this ultimately bounded Lyapunov functions, does that like count as like being less than or equal to negative c plus eta? Does that count as the what you had said before for like negative definiteness? That could allow the Lyapunov derivative to be positive, right?
Yeah, this one allows Lyapunov function. You know, this allows you to be positive. Yeah, that's right. As soon as c of x of t is less than eta bar, you go up again, possibly. Yeah.
So
yeah.
Wouldn't be. So we call this like ultimately.
No, but you know, I gave a definition of ultimate boundedness. This implies it, okay. And I could prove that for you. I'll give you the main idea. So this set here, the set of x which c of x is less than or equal to eta bar, that's a set you're referring to where we no longer get a negative right-hand side. But I'm going to add 1, make it a bit bigger. Okay? And I'm going to let t be yes, I'm going to give the main idea. So that's the thing. If I gave a very, very precise proof, it would take 40 minutes. Let's assume this is finite valued. We don't need to assume that, but let's just assume it. You know, just to, you know, it sounds like I'm assuming what I want to prove, but we could deal with that. The only way I should do is I should have put a min here of some big N to make sure this is finite valued. You know, I should. If this is infinity, I'll place it by N.
So,
yeah.
If we arrive at a Lyapunov derivative, we start with like a candidate and arrive at a derivative that has that form. Is that sufficient for saying the best it can be is ultimately bounded, or does that just mean that we haven't possibly done one?
Oh, yeah, no, of course. I mean, that's the thing is that we struggle. We find a Lyapunov function. It makes us smile. We get a performance bound. And the performance bound might be horrible. This number might be much bigger than you think it should be. Or maybe this is really 0. And actually, maybe forget this. I'm gonna let, this is an exercise. I'd much rather answer your question than go through this. It's in the notes if you like to. It's in the notes. You basically replace capital T by TB, and you just forget it. Well, I'd much rather answer this question. So what happens, in some contexts, you have a family of candidate Lyapunov functions, and you can come up with algorithms to give you the best bound. You know, that's a numerical procedure you might come up with. That's been successful in queuing theory and in some other contexts as well. Yeah, and very often it's an analytical tool. But what we're going to see is that understanding these big sorts of bounds is how we approximate dynamic programming equations for optimal control. You know, so we're going to have exactly the same sort of thing when we're looking at optimal control, and we're going to have a whole maybe family of approximation of inequalities like this when we really want inequality, and yeah. But as soon as I started that, I realized it's too hairy. Let's just look at one example. Before I do that, note suppose eta bar was 0. Then forget the average. So typically when you see this in a course in nonlinear control, you won't have this eta bar sitting there. You'll just have this, and you have the integral from 0 to t of the cost is bounded by this for all capital T. Well, that means I can set t equal to infinity. It's just the definition of an integral of an infinite domain. If I've got a bound like this for all t, then I can let t equal to infinity. And that's known as total cost. Forget that. Okay, so when you take a course in control, immediately they'll give you the total cost as a criterion. They never explain to you why you would even care about that. I think it's much, much more, this sort of criterion is much easier to appreciate in the stochastic control context. My gut feeling is that the reason this is emphasized so much in nonlinear control is because it has such an elegant, theory to support it. There's such a nice mathematical theory. Okay. So let's close with one example. I'm not sure you're going to consider this an example, but the linear case. So I'm going to use this with my notes. Hold on. Okay, so we have a linear system, x dot equals ax. A is a matrix. Okay, we have a cost function which is quadratic. So P, since I've said that C is positive definite, it means that P is a positive definite matrix. And I've said that V is coercive. It means that Q is positive definite. So this is strictly positive everywhere except, of course, x equals 0, and it's 0. So it's exactly the bowl shape that I showed before. And you can go through and you can easily work out this dot product. No big deal. What's the gradient of V? V, 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 V. It's 2qx. Thank you. And what's grad V of x dotted with f of x? Okay, so I take f of x, which is ax. That's the right-hand side. That's the velocity. And I have grad v of x. I just plopped it in. And then write this down. It's 2x transpose q transpose ax. But q is symmetric. Whenever you say a matrix is positive definite, you're assuming symmetry. Okay? All right, I mean, it's real valued entries. And I didn't have to take the dot product that way. I could have taken the dot product the other way. And I would have gotten 2x transpose A transpose QX. I can get rid of that transpose there, the same thing. All right. And it's also equal to 1/2 of that plus that. These are the same, so the average is the same. So do the algebra, you'll get x transpose and that's what we hoped is our Lyapunov function. This had better be minus c of x. All right. Well, if that's the case, this matrix has to be equal to that matrix. So the reason for doing this flowing around is that QA, it's not a symmetric matrix, and A transpose Q is not a symmetric matrix, but the sum is. Okay, and so you get a symmetric matrix. So there's hope that this could be equal to minus P. Yeah. What's that? Yeah. Okay. So if this is minus c of x as we want it to be, eta bar being 0, as it often is in deterministic models, then you have to have this symmetric matrix has to be equal to P. And that is, or minus P, and that's the Lyapunov equation. Okay, and so it turns out that this always has a solution, as long as the system is stable. So if the eigenvalues of A are in the strict left half plane, and some of you probably don't know that means stability. Okay, so having all eigenvalues of this matrix A be in the strict left half plane is the same as saying that the solutions to this differential equation decay to 0 exponentially fast from every initial condition. Because we know the solution. I mean, You all should have seen this somewhere, but maybe some of you haven't. The solution to this ODE is just a matrix exponential times the initial condition. And if the eigenvalues of A are in the strict left half plane, this thing goes to 0 exponentially fast. So stability, global asymptotic stability is the same as the eigenvalues being the strict left half plane, and that's equivalent to this having a solution. So there's a positive definite Q. Yeah, our wish came true. There's a positive definite Q for any positive definite P. And you can write it down. I won't bother. You can look this up in Wikipedia as well. There's a formula for Q. It's an infinite integral. It's very, very simple. We just were running out of time, and it wouldn't be very instructive, but you can just write it down. In fact, I think that is it, isn't it? 2:45 is our deadline. Okay, so there it is, all of nonlinear stability theory in one 45-minute lecture, and just this one important concept that v of x of t is decreasing with time, and in one case it's always decreasing, in the other case it's decreasing until you hit some set and then it just bounces around. Okay, and so that's the sort of thing we want to extend to stochastic models, and nothing will change. Well, luckily we have 2 hours next lecture, and we'll do all of deterministic optimal control theory. So because it's basically, if you're not going to go through all the proofs, I mean, I left some things out here. So, I mean, I've focused on the easy stuff that's the most relevant. If you do the same thing with optimal control, you can get the Bellman equations and get some insight like that. And it's really useful to do the deterministic case first, because it's much more intuitive than in the stochastic case, even though it's all the same. All right. So close. Just one comment. So Anand, I think, said this, but I just want to say it again. I rarely believe in optimization, and I do rarely believe in my stochastic models. Nothing is IID, and all problems have many, many things besides a single performance index. There's not one cost function that summarizes everything we care about. There's issues of risk and constraints and all sorts of things. The beauty of this topic is you get a whole huge collection of tools, just millions more than you could do in a deterministic setting. So all these cool Q learning, TD learning algorithms that could only have been inspired from the stochastic toys that we have to play with. Now it turns out they're useful in deterministic settings as well. So there's been actually a movement of concepts from stochastic theory to deterministic. But just as an incredible toolbox you get from stochastic modeling. But I just want you to know that, because a lot of people say, well, this stuff doesn't make sense, my noise isn't Gaussian. Well, to respond to them, your stuff doesn't make sense, friction's not linear. In deterministic settings, you make simplifying assumptions. I mean, I'm pushing this; it's not moving, right? There's static friction. It's really horrible. It's awful nonlinearity, and people ignore it in control design because they want to get a simple solution, and they might have to do some tweaks to make it deal with this horrible nonlinearity. That's the easiest example of something you have to ignore at first. So, even though I don't believe that anything I ever see is Gaussian. There are exceptions, but most of the time I don't. I'll assume it to get an algorithm, which I can test on a high fidelity simulator, and I'll have maybe two knobs to play with and get the best policy in that class. All right. I'll be able to narrow down my search for a good policy for control or inference or whatever. Right, so that's my philosophy in the course, all right? And everyone has a different take on this, so it's just my own personal view. All right, so next lecture, so I will post these notes very soon, And we will do the HDB equations in 2 hours. It'll be fun, I swear.